Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to finish off trusses by talking about a bit of an interesting topic, and that's zero force members. So like I kind of hinted to a couple times, what they love to do in the finals give you a very complex truss. And in that truss, they're going to ask you for some members, and long story short, some of those members are actually going to have no force at all. And there's actually a trick that we can find those members right off the bat without having to do any analysis. Now, if you guys want to do the analysis, that's fine. You'll come to the same conclusion that they carry no force. But by doing this, you can skip a lot of that work and just go right to the final answer. And again, with midterms and with finals, you guys know that's what you want. You want to be quick. You want to get right to the final answer and move on. You want to get those marks. So, with that being said, we're going to start covering these zero force members and other little tricks that I think that they like to throw in exams to kind of confuse you guys. Then there's quite a bit of them, as you guys will see. So let's begin. Alrighty, for this example, what we'd like to do is just try and find some of the zero force members in this truss. So normally this would be a question where they'd ask you to find some forces in the members, but we've covered the method of sections, we've covered the method of joints, and that's all you guys need to know for the final. Just those two methods, so it's pretty simple. But now we're going to cover what some students have a lot of trouble with, and that's zero force members. So what you guys will find out is that usually the first question in a final may say, what are the zero force members in this truss? And what that means is, what are the members in this truss that carry no load at all? So if we look at this truss right here, there's a lot of members. It's kind of hard to figure out what carries no load. So let's go to what they teach you guys in the lecture. And they give you two scenarios to find zero force members. And they both involve the joint of a member. So I'm going to draw two joints. So the first zero force member is when you have a joint and that joint has two members that come out on it. So one, and let's just say two. So only two. If this is the case and there's only two members and there is no external loads, then what that means are both of these members carry no force. Now this is kind of the trivial one. The very, very easy one. I've very rarely seen this one used because, again, it's very trivial. A lot of people know these won't carry any force. Now we'll get to the more interesting one. And this one right here is the one that they use to trick a lot of students. So for this one, there's going to be three members, and there's a trick to this right here. So we have two members here, and we have a third one. So the trick to this one is two of these members. So if we look at let's say member 1 and member 2, they're collinear. So what this means is this right here, 180 degrees. They run parallel with each other. And if that's the case, and there's no external load at this joint, and those two members run collinear with each other, then it means that this third member is zero force. And that one right there, that's the one that's going to kind of lead the way into all the tricks. So if we look at these two situations, and if we look up at the truss right now, we can actually use these two situations to find some zero force members. So I'm going to use this as situation 1 and situation 2. So first off, looking at situation 1, the only places in the truss that have two members are going to be points A. Oh, that's actually probably not the best color. Let's go to pink. It's going to be point A. Okay, well, if we look at point A, there's going to be some sort of support reactions there. Of course, A is a pin. So what we'd have is, oops, that did not turn out very well. So what we'd have is a support reaction in the vertical, a support reaction in the horizontal, something like that. So right away, we know that case number 1 doesn't apply because case number 1 needs no external forces. We look at the other location that only has two members, and that's going to be point G. So, but it's the same scenario. At point G, we have a roller, so there's going to be a vertical force there. That counts as an external force. Situation 1 does not apply. For situation 1, if we had an external force here, then those members will not be zero force. Everything goes out the window if there's an external force. So with that being said, nothing falls into situation 1. And it's very, very rare that you guys will see something that does fall into situation 1. It's situation 2 that's going to start creating the tricks. Now, let's go to situation 2. Well, the first part of situation 2 is three members. So if I look at this truss, I see point B has 3 members, and I see point F has 3 members. Where else can I look? Oh, point J has 3 members. So we got 3 situations in which we have 3 members. Now, if I look at this more closely, remember, one of the kind of the conditions of case 2 is that 2 of the members must be collinear, perpendicular. And if I look at J right here, none of those members are collinear. None of them. So from that alone, I can conclude that none of those are zero force members. I can't say that any of those are. But if I look at joint B and look at this member here, okay, well that's actually parallel with this member. So if that's the true, then I got no external load at B, check. 2 of the members are collinear, check. Therefore, the third member must be zero force. So that means that this member right here must be zero force. Now, if I go look at joint F, I see that I have the same situation. I got 2 collinear members at the bottom like this. There's no external load at F. Therefore, the third member, which is HF, is going to be zero force. So it's as simple as that. And if you guys want proof of this, let's draw out joint F and just see what happens. So if I look at joint F, so I'm drawing the point right here. I know I got 2 members that come out collinear with each other, like this. And then I got the third member kind of going straight up. So I'm just going to label these real quick. I got FG on the right. I got HF on the top. And then I got EF on the left. Okay. Well, if I was solving this using the method of joints, and I take sum of the forces in the y direction is equal to 0, well, I'd have HF, and that's it. And we know that since it's an equilibrium, everything must equal 0. So therefore, HF is equal to 0. So instead of analyzing that joint, we can just look right away and say that one's zero force. So those are the 2 cases they teach you. And especially when I was taking this course, and let's say this was my final exam question, I'd say, okay, I would have done everything that I just did. I would have said LB is 0, HF is 0. Nothing else really works into those 2 cases, so that's it. 2 zero force members. Now, this is where the tricks come into play, right here. So if I look right here at joint, I'm going to go to purple this time, joint H. We didn't look at joint H before because case 1 you need 2 members and case 2 you need 3 members, and joint F had 4, so we didn't care about joint F before. However, now that HF is zero force, so this one's zero force, joint H now actually has 3 members. And if we look at those members, IH is actually collinear with HG. So we can conclude that HE is actually zero force as well. So this is where the tricks come into play. No, I know when I wrote the final exam, I didn't consider that whatsoever. So when you conclude that something is zero force, such as HE, you have to reanalyze the joints because some of the joints might disappear. And if you guys aren't sure exactly what I'm saying, well, let's look on the other side at joint B. So from joint B, we concluded that this member right here in red, LB, was zero force. So that one's gone. And now if we look at joint L, so this joint right here in purple, it now only has 3 members, AL, LK, and LC. And if we look at AL, we see that it's actually collinear with LK over on this side. So we can conclude that the third member is actually going to be zero force. So this member right here, this one's going to be zero force. So just like that. Okay, well, how exactly do we prove it? Well, let's go down here, and we just did joint F, and from that we concluded that HF is 0. So let's move up to joint H now, based on what we know from joint F. So we come up here, and I draw joint F right here, or sorry, joint H. I know that I got two members that run like this. So I'm going to just put little arrows. Let's label them really quick. So these members are at the top, and that's I, H, and HG. So we got I, H, HG, and I should actually put joint H, just so everybody knows exactly what I'm doing, or else I'm going to lose all of you. And we see that there's an additional two members right here. So this one comes out like this. And we have one that kind of goes straight down like this. And we know that this one is HF. And if we look up here, we know the other one's HE. So this is when a lot of you guys are going to say, okay, Clayton, Mr. Smart Guy, if I do sum of the forces in Y, I got 4 unknowns. If I do sum of the forces in X, I have 3 unknowns. I can't solve for anything. You can't prove anything. Well, this is when the trick comes into play, that you guys can define your own axis. So what I can do is, instead of having the regular XY, I can have an XY axis that goes exactly like this. And if you ever want to prove zero force members, you guys can use this axis right here. So looking at this axis right now, and if I were to go sum of the forces, and what I'm going to do is I'm actually going to call them, just so none of you get confused, y prime and x prime. So if I were to go sum of the forces, and y prime is equal to 0, well, what I would have is some components of HE, so negative, since it's pointing downwards, times some component of HE, minus some component of HF is equal to 0. Okay, well, this doesn't prove anything. Got 2 unknowns, whatever. But we know that HF from up here, so I'm going to just draw a quick little line. We know that HF is actually 0. So if we substitute that into the equation, we're going to get minus something times HE minus 0 is equal to 0. Well, that minus 0 means nothing, so let's get rid of that. Therefore, negative something times HE is going to be equal to 0. So therefore, HE must equal 0 as well. So in this question, there's actually 4 zero force members. But I know as a student, I would have only been able to pick 2 based on the cases. So kind of the trick is, if you do find a zero force member, get rid of it from the diagram and check if the cases apply again. Because once we get rid of LB, then if we look at joint L, we can see that there's only 3 members now. And then we can go back to case 2. So that's it for this diagram. I think that that covers the trick. So in the exam, again, if they show you guys zero force members, once you solve them using these 2 cases, cross them out of the diagram and reanalyze the truss and try and find these cases again. Most of the time you guys will typically be able to find some more. So thank you guys all so much for listening, and I'll see you guys next week when we go into internal forces, which is actually pretty easy next week. Next week's an easy week. The week after, going to get a little hard, but who cares? We're just going to focus on next week. So thank you guys so much. I'll see you guys in the next video.